Hello, ladies and gentlemen. Let's have a little lesson here on section 3. So, we're talking about the nature of matter. So, in chemistry, we are studying matter and how it changes. That's the definition of chemistry. So, what matter is basically anything, it has mass and takes up space. So, what we're really wondering about in chemistry is what's happening to that matter with the molecules and the atoms. How are they changing in chemical reactions? So, the chemist's view. So, for us, the macroscopic world, that's the ice you can see, right? Then there's the particulate world, like little particles of water. And we talk about the symbolic world. So we can't see it, but we have these symbols to represent one oxygen combined with two hydrogens to make water. So the macroscopic view for us would even just this petri dish is big for a chemist. And then particulates, we talk about little particles. So if this is a balloon filled with hydrogen and it's surrounded by oxygen molecules, right? And then what's going to happen in a reaction here is that if you bring this flame over to it, the balloon's going to pop. These hydrogens are going to break apart. The oxygens are going to break apart, and they're going to reform into these water molecules. So we write that as this symbolic formula. We say two hydrogen molecules plus one oxygen molecule produces two water molecules. So there's the symbolic part. We've already seen these pictures in the earlier section, but here we talk about the kinetic nature of matter. So we talked about energy, and matter consists of atoms and molecules which are in constant motion. So they're always moving. Even these ones in the solid are just vibrating back and forth very quickly, but not far. They appear to be in the same spot all the time, but they really are moving and vibrating. You give them more energy, and they can move faster, then they'll turn into a liquid. And if you give them even more energy, they'll break any interactions that are going on between them and float away as a gas, right? So, states of matter. We have solids. These have rigid shapes and fixed volumes. So the shape doesn't change, the volume doesn't change if you move it from one container to another. The external shape might reflect the atomic and molecular arrangement. So the way those little particles come together can affect the shape of it. And we have a reasonably good understanding of solids. Now, liquids have no fixed shape, so they're going to take the shape of their container, and they may not fill the container completely. So, just because you fill it with a glass with water, it doesn't fill all the way to the top. It just stays, whatever volume it is. So, now the note here that says they're not well understood, you might think, well, Miss Rector, I think I understand how liquids work. But we do have a lot of things that if you ever made like oobleck or something in your classes before, where sometimes it's a liquid, sometimes it's a solid, sometimes we have some things like non-Newtonian liquids that don't really obey the rules that we've put out there for liquids. Then there's gases. Gases expand to fill their container, so their volume changes, right, as the container you put it in. So the bigger, you're never going to walk into my classroom and walk into one corner and there's no oxygen or no air there, right? The gas in the room is expanding to completely fill the container. And we have a pretty good theoretical understanding of that. We got a lot of gas laws we're going to learn next semester. So, other states of matter, you might say, well, there's others. Yeah, there's some others. In fact, the most common state of matter in the universe is plasma, and that's because the sun and the stars, all those stars you see out at night, all through the universe, are examples of plasma. So it's like if you had a gas and you heated it up so much, it actually got electrically charged. So some of the electrons left it. So it becomes a plasma. So here on Earth, you can think like lightning, or if we were in the classroom right now, you'd see me playing with a plasma ball. But of course, I'm not going to do that on here because if I do get the plasma ball out when you come back, you don't want your electronics near it. You'll see why. And then there are some other things that we're not going to go too into in this class, but Bose-Einstein condensates. These happen near absolute zero, so you don't run into that stuff every day. You get these superconductive properties of things. All right, let's talk about properties. So, physical properties are um, things that you can observe without changing it. So, color is an example. I can look at the color of something and I haven't altered it, I've just observed its color. Melting point, boiling point. I can take ice and melt it and I haven't changed anything. I can see that it melts at 0 degrees Celsius and I can see that it boils at 100 degrees Celsius and it's still water. I haven't changed it chemically anyway. The odor, now, this is tricky. Just the fact that something has an odor is just its physical property. So, sulfury things with sulfur in them tend to stink like sulfur, right? That is a property of sulfur, just its physical property. It smells funny. Now, if something changes its odor, like it didn't stink and now it does, that's different. That's a chemical change going on there, or sign of a chemical change anyway. So let's look at something like graphite. So if you have a pencil, you've probably got some graphite in it. That's what pencil leads are made of. And it's really just carbon. But the structure of those carbon atoms is going to determine the physical properties. So that graphite in your pencil, it's like carbon in like little sheets just sort of laying on each other. So as you go writing along your paper, little sheets of carbon are being left behind. That's what makes it good for pencil lead. Now, this same carbon, if I took the same carbon in that graphite and put it under lots of heat and pressure for a long amount of time, these might get intertwined in a different way and make a diamond. So the graphite in your pencil lead and the diamond in your diamond ring are made of the exact same stuff. It is just how they're structured that makes them have different physical properties. So let's talk about physical changes. So again, physical properties are things you can observe without changing the compound itself. And physical changes are the same thing. We can observe a physical change happening, and it does not mean it's a new thing. It still has the same identity. So boiling a liquid, melting a solid. So if we boil water, that steam coming off, this stuff right here, that's still water. It hasn't changed. It's still H2O. It's just the particles are further apart, right? So solids, liquids, melting, boiling, those do not change it. One thing that tricks people sometimes is dissolving something in a liquid. So if I put a bunch of salt in some water, the salt, stirred up real good, it seems to disappear. And you're like, oh, it's chemically changed. But no, it's just dissolved. Just the water has surrounded those tiny little salt particles. If I were to boil the water, I could get the salt right back if the water evaporated. That is just making a mixture. So a solution is when you have a solid dissolving in a liquid. And if you get a homogeneous mixture, then it's called a solution. Chemical properties, on the other hand, are something that is going to change the substance. So to observe a chemical property, I'm going to change the substance. So, for example, if I want to see if something's flammable, that's a chemical property. What am I going to do? I'm going to burn it. Well, now it burns. It's flammable, but it's no longer the same thing it was anymore. So, if you burn hydrogen in oxygen, like we did with the balloon here, now this is a chemical change. Here it was hydrogen, and these were oxygen. Now, here we have a new substance created. That is going to be the key to a chemical change. You know a chemical reaction has occurred when you have a new substance created. So you've transformed from these molecules to these molecules. They're different now, they have different chemical properties. So, what are some signs that a chemical change has taken place? Well, if it's given off heat, there's probably some bonds being broken and reformed there. So, that's a good sign that a change has taken place. Light, if it gives off light, that's also a good sign a chemical change has taken place. It's usually a form of energy coming off, like heat. Okay, if it's producing a gas, but it's not boiling, so water being boiled, you might think, well, it's bubbling and steam is coming off, but that's just boiling. I'm talking about you put two liquids together and suddenly it starts bubbling, right? It's not any hotter. You didn't add any heat to it. It's just got bubbles coming off. That's probably a gas being produced from a chemical reaction. And then there's something called a precipitate. So, a precipitate is when a solid forms when you mix two liquids together. When we get to the lab, we'll see an example of that happen. You pour two clear liquids together and you get this sort of white solid that forms. On here. So, here are some examples of reactions. You know what? I'm not going to do that right now. Just move on with this. It'll take a while. Chemical versus physical. So, for example, a melting point, that is a physical change. If something is flammable, then it's a chemical property. Density, I can observe the density of something. I can take the mass and the volume of it and do that calculation. That's just a physical property. If something's magnetic, I can observe that without changing it. So that's a physical property. Tarnishes in air. So if it's tarnishing, it's changing colors usually, that's a chemical property. So chemical versus physical. Let's see. Rusting iron. So the iron is rusting, it's combining with the oxygen in the air, making something new and different. That's a chemical change. You dissolve something in water. We said that would be physical. You burn a log. Now that log is no longer the same thing, right? It's ashes, it's had a gas come off of it, you felt heat and light. That was a sign a chemical change is happening. Melting ice. It's easily reversible. I can freeze the ice right back, so that's a physical change. Grinding some spices. What do we do? We can't necessarily ungrind the spices, but that doesn't mean they're different than they were. They're just like chopped up. All right, so we'll stop there and have a good day.